Here are the solutions to the three problems that were on the quiz on Friday. The first side of the page, we were looking at volumes. And so if we follow the bulleted steps to go through this, we're going to label the points on the end with a common x vertex called x. The point on the bottom has a y-coordinate of 0, regardless of where the x is. And the y-coordinate of the curve on the top is whatever the equation is, 2 sine x. So that's how the top and bottom of that generic slice is labeled. Since we're finding a volume, we add this extra step of sketching what one piece looks like. So if I think about the shaded picture as being my loaf of bread that I'm looking straight down on, then this is just taking one piece out. And if I take that piece out and lay it down so I can see its face, it'll look like this, a very thin wafer. So the edge here, the edges there corresponding to this stick. So this stick is ending up here like that. So it's square. We're told that it's square. And so I need to write down the volume of one slice, and the volume of the slice is going to be the facing area that I see, and the facing area that I see is just a square, so it's whatever the measurements are along here squared times the thickness, and the thickness I would represent as delta x. Now the sides, what I need to do is realize that the length of the side of my square that I pulled out, so the length here is exactly the length here. Those are the same thing. And up in this picture, it's easy to measure the length of that because those are two vertically oriented points, and so the length of that stick is going to be just the difference in the y-coordinates. So the height of that of that rectangle in the 2D drawing is 2 sine of x, and so that's how long the sides are, both sides in this square. So the volume is going to be the side squared, so 2 sine of x is the side measurement squared times delta x. Since that's the volume of a single slice in terms of a variable x, then the total volume is going to be the sum of all of those things. And we know that when we do the integral, we change our delta x to dx. The limits of integration are just all the possible x values. We're told that the x values range from 0 to pi. All right, in this one, everything is the same except the solid that's being formed is the one that we get by spinning the picture that you see around the x-axis. And so when that happens, you're going to get a cone shape. And the most significant thing is to be able to draw a picture of what one slice of that three-dimensional cone looks like. So before we do that, let's do our steps where we label everything in the 2D picture that we can. This is 5 minus 5/3 x is the formula for y-coordinates of that point. And just like before, the y-coordinate of the point on the bottom is always 0. So what we talked about in class was that rather than spin the entire region and then think about slicing that region, what we can do instead is think about what does it look like when I spin just the little stick that you see drawn there around the x-axis. And when you do that, if you spin that around, it'll look like this with a little bit of thickness to it. And the radius of this disk is exactly the length of that stick. So those two things correspond to each other. So once I understand that that's what my one slice looks like in the 3D solid, then I can just write down the formula for that volume. So the volume of one slice is pi times the radius squared, because that slice is a circle, times the thickness. So again, it's always the facing area of the piece of bread that we pulled out times the thickness of the piece of bread. So pi r squared times thickness. So, and the way we drew it, we can see the radius is just the length of the little stick in the original picture, and the length of that stick is just the difference in the y coordinates. So the total volume is going to be the sum of the slices over all possible values of x, and you can see in our picture that the values of x run from 0 to 3. So neither of these volumes, neither of the solids that we're generating here had holes in the middle. That's a different kind of problem slightly. You can use the same kind of formulas, but that's the nature of the problems that you're doing for your outside of class assignment this due Tuesday. So hopefully you'll have some experience doing that from that assignment. To find area, it's a lot easier because we don't have to do any kind of visualization in 3D of what one slice looks like. So if we follow the same process, in this case, these points are horizontally oriented, not vertically oriented. And so determining the location of a slice would be a matter of specifying a y coordinate. So that tells us that we're going to have to set this entire problem up in terms of y. The curves are given, the first curve, the parabola, is given as an equation x equals y squared, and so that works out really well because that really means the x coordinate is the y coordinate squared. So the point on the left has an x coordinate that's equal to the y coordinate squared, and we can just write that in. The other line that's given is not solved that way. It's given y equals x minus 2, so I would need to take a second to rewrite that by adding 2 to both sides, and I would have this. And so now that also has the form x coordinate is equal to something about the y coordinate. So in this case, that equation is saying the x coordinate on this line is always the y coordinate plus 2. So that's how I would label the two ends of that, that little slice. Drawing separately the slice is not all that interesting because it doesn't really look any different. This is the slice. And the only reason I'm asking you to draw it is so that we get in the habit of drawing one piece by itself, but it's really more useful for the three-dimensional problems. Once I have one slice, I need to answer the question about that slice. Now in this problem, the question is area. So the formula for area of a slice is going to be, it's roughly the area of a rectangle that has those dimensions. So rectangle is going to be its length times its width. The width, the skinny direction, is going to be a small change in the y direction, so we label that delta y. That's not all that mysterious. We need every single thing in the setup to be in terms of y, so it would not make any sense to try to put a delta x into this problem. The length of that stick is just the difference in its x coordinates. So it should be the bigger x coordinate minus the smaller x coordinate. And so the way number lines are oriented, that's the rightmost x coordinate minus the leftmost one. So it's right minus left because numbers get bigger going right on a number line. So that's the right the right x coordinate minus the left x coordinate. And that area will be correct regardless of which values of y, which value of y that we pick. That means the total area is just going to be the sum of these. Again, the delta y turns into dy when we do the continuous sum. I do need to know what the values of y can possibly be in my picture. In this one, they seem to hit the lattice points pretty well. So those seem to be the smallest possible value of y and the biggest possible value of y. If you can't tell, don't forget that you can just simultaneously solve these equations to figure out where that happens. We have x equals y squared and x equals y plus 2. And so for both of those to be true at the same time, it would mean that y squared and y plus 2 have to be the same. That's the only way they could both be equal to the same number x. And then y squared equals y plus 2 can be solved using our normal tools for solving polynomial equations. And so if we do that process, we'll see that the smallest y value really is -1 and the largest y value really is +2. But that's what it looked like. So that would be good enough.